this afternoon session. And we are very happy to have Victor Rodriguez from Princeton University. And he's one of the recipients of the Frontier of Science Award. And he will tell us about the work. Let's welcome him.
Well, let me begin by thanking the organizers of this conference. It's my first time here at BIMSA, as well as first time in China, so it's truly an honor to be here. And today I'll tell you about this paper, listed here in green, in collaboration with Bruno Balthasar, as well as Qi Yin. And the title of the paper is the following: CC instantons and the non-perturbative dual of C=1 string theory. Okay, so most of the talk, the context of this talk will be in low-dimensional string theory. So perhaps the most familiar examples of string theories are in 10 dimensions and have supersymmetry. But the theory that we'll discuss today, it's in the opposite extreme. So it's a theory in only two-dimensional, one time and one space. And the point of doing this, of studying this, perhaps also unrealistic theories of string theory, is that they're much simpler than their higher dimensional counterparts, but they still exhibit very rich phenomena. And the hope, of course, is that we can learn lessons in this simplified context that apply more broadly in string theory. So for today, low-dimensional string theory will be our theoretical laboratory to understand more basic facts about string theory. So here I just listed a few examples of what kind of phenomena occurs also in this low-dimensional examples. The first one is, of course, that they are early examples of holographic as well as stringy dualities. They also appear in these low-dimensional models. The subject of today's talk, non-perturbative effects, in particular, the class of effects mediated by the instantons. They also occur in 2D string theory. There's also very nice examples of time-dependent phenomena, which is a difficult subject in string theory, but there are examples in which this can be analyzed in detail. And finally, a slightly different flavor, these two-dimensional strings also serve as models for 2D quantum gravity. Although this last point won't be much discussed in this talk. Okay, so with this sort of introduction, here's a brief outline of this talk. So first I'll describe, without actually focusing on any particular theory, I'll describe roughly how the on-shell worldsheet formalism works to compute a class of non-perturbative effects. So, so the first part of the talk will be mostly pictorial, and that will be enough to just get the basic idea of how this calculus works. And the second part of the talk will get a bit more technical and actually apply such a formalism to the particular theory of 2D strings. And at the end, I'll compare the results that we get with a dual description in terms of matrix quantum mechanics. So I should say that today I won't talk too much about the holographic duality itself, but mostly it will be in the back of our heads as more as a check that the string theoretic calculations that we will do are correct. Okay, and then we'll end with a short discussion of recent developments as well as prospects. Okay, and then of course, not right after, but a little later today, Ashok Sen would also talk about this type of non-perturbative effects. Okay, so you should stay for that as well. Okay, so let's begin. So let's start with the on-shell worldsheet approach to calculating this instantonic effects. So let me phrase the basic elementary question that we wish to study. So perhaps one of our favorite type of observables that we discuss in quantum field theory, or as well as in string theory, is the S matrix of particles, or in this case of strings. So we arrange two strings, we arrange them to collide or get near each other and interact together, and then with the strength parameterized by the string coupling, and then go off to infinity in the asymptotic regions, again like this. Okay, so as we might be familiar, there's a very nice formalism, the worldsheet formalism, to compute just like Feynman diagrams in quantum field theory, we know how to compute this in string perturbation theory with this sort of fat Feynman diagrams. But more precisely, this worldsheet diagrams that are in perturbation theory, loop corrections, quantum corrections to a given scattering amplitude are modulated by this small parameter, the string coupling GS. Okay, so this is perhaps familiar that we learn in textbooks that given, for instance, this 2 amplitude as a function of the Mandel variables S and T, it admits this genus expansion in even powers of the string coupling. Okay, so the basic, the elementary question we wish to study is, are there further corrections to this expansion and that are non-perturbatively small? So by that, I mean exponentially suppressed in 1 over exponential 1 over G string. Okay, these have long been anticipated by the properties of this genus expansion, and these are mediated by d instantons. Okay, so today we'll see how we actually compute these type of corrections to the scattering of closed strings of this form. Okay, so here's the basic picture. So turns out that we can adapt a little bit the worldsheet diagrammatics to still capture this non-perturbative effects. So the basic idea is to, instead of consider closed Riemann surfaces, which are the fat Feynman diagrams, we compute diagrams with a boundary like this, very similar to deep range scattering, but I'll highlight a few differences. So again, the punctures are where the strings come in and the strings come out. And the boundary condition on this boundary is the instanton boundary condition, which broadly speaking is of Dirichlet type, and like a deep ring, but for all non-compact directions or worldsheet fields, including the time direction. So it's an instant in time. Okay. But even at this point, I can, just by Euler counting, can see that the leading order contribution does not come from the previous diagram like this, but actually comes from a single disk 1-point function. So just to give the counter really quick, the disk in the usual normalization conventions comes with a factor of 1 over G string by Euler counting, and the vertex operator itself comes with a factor of G string, so that the whole thing multiplying these is of order 1. So this is in fact the leading order 1. And the prescription is to multiply this disk 1-point functions all together like this for n, a product of n of this disk 1-point function. The picture that I'd like to keep in mind is that even though this looks disconnected, it's the picture in target spacetime is the following. So the instanton is an instant in space and time. So at a particular point in space and a particular point in time, the instanton occurs, and that the space-time coordinate of which the instanton occurs is called the collective coordinate. Okay, and since we chose a particular point in space-time, and this is the pictures where this is where the string comes in and the string comes out and the scattering amplitude. And since we chose a particular point in space-time, we break Lorentz invariance with a particular d instanton. So we don't expect individual worldsheet diagrams to conserve energy momentum. So that's why we consider disconnected product of this worldsheet diagrams. But at the end, we're instructed to integrate over the position of this collective coordinate, in this case, all of space-time. And after integrating over this collective coordinate, we recover energy conservation of the scattering amplitude, just like the perturbative pieces. Okay, so that's a prescription. Okay, and we will see how this explicitly works in the context of 2D string. But for now, let's keep it generic. But now that we know that we can, we're supposed to consider disconnected diagrams, there's an obvious class of disconnected diagrams that one can consider. And these are empty disconnected diagrams. So for example, we consider an empty disk or a product of 2 empty disks with an appropriate symmetry factor, and so on. We can do the same for higher ontologies, higher genus. For example, the annulus is next. And they also consider many product studies. So we see that these exponentiate very nicely in the following way. So we get the exponential of the empty disk diagram, of the annulus diagram, and then higher topologies. And again, by Euler counting, we know that this first one, the empty disk diagram, goes as 1 of the string. The next one, the annulus diagram, empty annulus diagram, goes as G string to the 0. In other words, the 4 to 1. So these have the very nice interpretation, this empty diagrams, as providing the exponentially suppression factor of e to the -1 with the string, which we interpret as an instanton action. And for instance, the following one less power of G string, this one, this is a 4 to 1, is simply a constant that we might want to think about as a renormalization of this instanton action. So these exponentiated diagrams are the ones that multiply, they factor out of every worldsheet diagrams where the actual closed string insertions replace. Okay, so let me summarize. The leading order contribution to the 1 to n scattering amplitude takes this form. So it's the disconnected product of this one-point functions in leading order with these two exponentiated empty diagrams. Okay, so that's the leading order term. We can further consider two generalizations. For instance, we can consider sub-leading order in G string, which we'll do in the next slide, or as well contributions from a configuration of several instantons. This one was a single instanton. We can also consider configurations of more instantons, contributing to the same one-to-one amplitude. Okay, let's see how that works. We can even go a little further. And shortly after describing that, we'll explicitly try to evaluate this type of diagrams in the example of two-dimensional string theory. Okay, but let me talk first about the sub-leading order of G string. By sub-leading order, I mean still suppressed by an exponentially small suppression factor like this, but further suppressed by an extra power of G string. Okay, so well, there's the two more diagrams that we need to consider is corrections to this one, which contribute to leading order. So the two next empty diagrams, which is the two-fold this or the torus with one fold, which by Euler counting, they are suppressed by 1 power G string, like this, as well as higher topology diagrams, which have the actual vertex operator insertions, the closed strings. So for instance, this 2-point function and the annulus 1-point function. Okay, so the diagrammatics is the following. So we still have the instanton action and the normalization factor, the exponential of the empty diagrams, together with the disk 2-point function and the annulus 1-point function times the disk 1-point function, plus the permutations for the two closed strings, as well as the product, the leading order contribution times this empty diagrams that we just expanded the exponential for to contribute to this. Okay, so this is the subleading diagrammatics. And already here, we can notice something kind of interesting, or anticipate a little bit, that it will turn out, as we'll show later, that in certain regions of moduli space of these diagrams, namely in an open string channel where there's a degenerating strip like this, for instance, in the 2-point, it becomes this shape, or the annulus becomes this shape, which we think about it as this like being the channel in which there's an exchange of an open string. Turns out that there's divergences when a massless or a tachyonic mode propagates in this degenerated strips. But what is nice is that the instanton calculus is that this is the first, I like to put it as one reason in which string theory is smart is that you're instructed to sum over all these diagrams, and the divergences that occur in individual diagrams, once you add them all up, precisely cancel, rendering the amplitude finite. Okay, but let me also advertise here that, in fact, since it's a logarithmic divergence for a massless open string mode in this case, you might worry that there might, even though it cancels, there might be a finite ambiguity in this cancellation. So in practice, if you want to regularize this type of diagram, if I put a cutoff on, say, the worldsheet modulus here, if I want to cut it off with a small size epsilon, and you wish to cut it off with a size of 2 epsilon, will differ by a constant ambiguity. So that from this worldsheet diagrammatics, there's no way, to, at least not that I know of how to fix unambiguously that additive constant. But then it was later realized by Ashoten that this is unambiguously fixed by phrasing this diagrammatics in full string field theory. So hence this is why I say string field theory is even smarter. That's true. I don't think so, but I don't think I have a quick answer of why not. It's maybe once we see the exact form of the divergence, maybe we can discuss it again. But I don't think it can be. Oh, Afro has a. That's another good point. Somehow it doesn't seem natural because it'll mix the perturbative expansion. Yeah. So that appears, but there's all the one that leads to a long divergence is the is partial x0 for the prequels. So it's a massless. You can think about it as translates the collected coordinate. Okay, so that we'll see explicitly a little later. Okay, so this is one nice feature of this. The next generalization I wanted to mention, even though I won't discuss it too much, is the correction to several instantons. In this case, I'm showing the 2 instanton contribution to a one-to-one scattering amplitude. There's also a nice diagrammatics. Now we have 2 types of 2 instantons, position 1 and position 2. Here's the empty diagrams. So there's 2 of them. So we have a factor of 2 that's further suppressed. And then 2 factors of this normalization constant, like this. And the picture I like to keep in mind is, for instance, we have 1 instanton at one position x1, a second instanton at position x2, where the string comes in and the string comes out. And well, they look separated, but the way I like to think about it is they're still connected through this annulus diagram that connects the first instanton to the second instanton, for instance, through an open string or a closed string, like this. So this is a picture I like to keep in mind of the spacing. Okay, so this is perhaps a second reason in which string theory is rather smart. So worldsheet diagrammatics precisely give you the measure of integration, namely this exponentiated diagram with 2 different instanton boundary conditions. So this is the measure that comes out, and this is the correct measure to integrate over this collected coordinate space. Okay, and we will compute it in an explicit example, but it depends non-trivially on this distance between the instances. Okay, so those are the two other generalizations. But just to summarize, the structure of the 1 to k scattering amplitude, like this. Here I really have 2D string theory in mind, but this also generalizes to other string theories. So we have the usual perturbative expansion of the amplitude in even powers of the string coupling, which we learned from textbooks. The sphere, torus, the genus 2 surface. Then this is the contribution that is suppressed by a single instanton suppression factor, and a whole perturbative series with all powers of the string coupling, which we discussed a little bit. So the leading order one is just a part of the 1-point functions. In the sub-leading order, which has more interesting diagrammatics, together with some cancellation divergences. And yeah. sphere two-point function. Yes. So you're supposed to divide by the more proper way to think about it is to divide by the partition function of the whole closed string, and those would cancel out the closed string improvements. So it does not contribute at this order. Thank you. And then well, this is, I just selected one of these here just to emphasize the diagrammatics, but of course we can do this for any instanton sector here, which is slightly more interesting diagrammatics as well, where this non-trivial measure becomes part of the story. Okay, so this is the general structure, and yes, hopefully it's clear. Now we'll go into the specific context to see how do we actually perform, to see whether the instanton calculus actually works. And our testing ground would be this low-dimensional or two-dimensional string theory, also known as equal to one string theory. Okay, and we'll use that duality with the matrix quantum mechanics as a check that this calculus works. Okay, so now let me get a little bit more into the weeds of what this 2D string theory is, slightly more specifically. So it's a fully consistent and critical bosonic string. So no supersymmetry, it's only in 2 dimensions. And the first ingredient, perhaps familiar, is a time-like free boson, the worldsheet field that we interpret as time, space-time. And then this is slightly more complicated ingredient, Liouville CFT at central charge equals to 25. Let me give the field the name phi, which is the field that we interpret as the space of the theory. Plus, together with the conformal ghost, this system has a total central charge of 0, so it's a fully consistent string theory. Okay, so let me just briefly describe this in an abstract conformal field theory sense, just so that we know that it's an explicit theory. So more broadly, Liouville CFT, it's a non-compact and unitary CFT, more broadly parameterized by the central charge, 1 plus 6, and this other parameter b, plus b inverse squared. But the relevant value for here today would be b equals 1. So that is the central charge equals 25. And as an abstract CFT, the way to describe it abstractly, the so-called bootstrap definition of this theory, I'm supposed to give you 2 pieces of data to fully specify the conformal field theory in 2 dimensions. The first one is the operator spectrum, which in this case, in this theory, is fairly simple, just Virasoro primaries, scalars, with the following weight, 1 plus p squared, where p colloquially is referred to a Liouville moment. The second piece of data that I need to specify for the conformal field theory is, roughly speaking, the dynamics of this vertex operator. So the 3-point functions, more specifically, which were famously bootstrapped by Dorn, Otto, and both Samologicos, as well as Effer, into a beautiful formula that is now known as the DOCC formula. And I put it here in gray, so don't pay too much attention to it, but just remember there's an explicit function. But once I specify this 3-point coefficients by conformal symmetry, we can, at least in principle, compute any correlation function, higher point and higher Riemann surfaces in this CFT. So it's a totally explicit theory. Okay, so back to the full string theory. The physical states of the string theory are built from these ingredients. So a plane wave in the time-like free boson with a plus minus signaling the incoming or outgoing flow string, together with a vertex operator in Liouville CFT, precisely at this value of its Liouville momentum, satisfying the on-shell condition that this be a 1,1 vertex operator. Okay, we can also see that if we read off the mass squared, by which I mean negative omega squared, where omega is the energy, plus p squared, it is 0. So in fact, the lowest, this is the only propagating degree of freedom in this theory, and it's a massless state, like this. And this is it actually. So unlike higher dimensional strings, which have an infinite tower of stringy modes, this 2D string theory is a little simple, in which this is the only propagating degree. Okay, so let me just give one more slide just to give a bit more physical intuition of what this theory describes. And for that, I want to write down the classical action of Lugos CFT in here. So this is a kinetic term for the field. And let's first look at the linear dilaton piece here. So if you remember, the whatever multiplies the dilaton field is what controls the string coupling. So the string coupling goes as e to the 2 pi. So this means if we interpret phi as being the coordinate of the space, so this means that the string coupling, when phi is large and negative, the string coupling is very weak. And in the other extreme, when phi is large and positive, then we have very strong coupling, exponentially strong. But then it comes the purpose of this so-called Lugo wall term, exponential factor here, which shields this potentially uncontrolled region of space. Okay, like this. So the basic physics to keep in mind is that the vertex operators, the physical vertex operators that I wrote down are nothing but plane waves that come here, interact with each other where the string coupling is non-zero, bounce off this potential wall, and then go back to the asymptotic region, like this. And of course, you can compute just the regular scattering amplitudes, just the closed strings, in string perturbation theory as an exercise through usual techniques. Okay. But today we want to study non-perturbative corrections in this theory. Okay, yes, so briefly I want to just mention the dual theory of this two-dimensional string. It's an early example of holography. So it turns out that this theory was discovered to be dual to the following model. So it's matrix quantum mechanics. So it's n by n matrix M subject to this inverted quadratic potential. In the interest of time, I won't describe this too precisely, but following some standard procedure of diagonalizing this matrix, we can rewrite this Hamiltonian system into the following. So diagonalizing in terms of the eigenvalues of the matrix M, we can write it down as absorbing so-called van der Monde determinant that you pick up while doing this diagonalization. And we get the following Hamiltonian right here, which is a free Hamilton, well, sorry, a Hamiltonian, a sum for all eigenvalues with the same potential. So it's non-interactive because we're just summing over all n of them. And they're fermions since we absorb this antisymmetric factor van der Monde determinant to the wave function. So the two highlights I wanted to say is that we have a system of non-interactive fermions subject to this inverted quadratic potential. And the second highlight is that there's a further, to make contact with the string theory, there's a further double scaling limit, which we can think about roughly as, for example, just for the sake of this slide, we can add a quartic potential to make it bounded. And the double scaling limit is a precise limit in which, well, what the fermions do subject to a potential, they start filling up Fermi levels like this. And the double scaling limit is to take the number of fermions to be infinite at the same time as taking this quartic coupling to 0, just to make it infinitely deep. So after the double scaling limit, one ends up with a picture like this, where the fermions fill up this whole Fermi sea up to this Fermi level mu. So in the dictionary, so this parameter mu is mapped to 1 over G string, this duality. Okay, so the reason I wanted to bring up the dual, even though it's not the main point of this talk, is that, one more comment. Just as a side comment, the perturbative excitations of the Fermi surface are what are dual to the closed strings from the string theory description. Okay, the main point is that from this picture, it becomes a little clearer why we expect non-perturbative corrections to closed string scattering amplitudes. In this language, from the dual language, this corresponds to tunneling of fermions from this side of the potential to the other side. You can even estimate the transition rate through a simple WKB estimate. And it goes as e to negative 2 pi mu, where mu was this distance. And using the dictionary, this is it gives this exponentially 1 over G string suppression factor. So signaling the existence of the instantons from the string theory side. Okay. The second point of why I wanted to bring up the dual description is because for the purposes of today's talk, the matrix side of this holographic duality has been completely solved, even non-perturbatively. So there are, for example, by some work by Plesser and Rambula, they can compute any scattering amplitude non-perturbatively in mu through some formulas here that I won't describe, but hopefully they're a little bit intuitive. But the main point is that at least we know explicit answers that we can hope to compare to. So here I've just given two, which will appear later. The 1 to n scattering amplitude from the leading order. So by this, I didn't put it here, but it's, oh no, it is here. So suppressed by 1 of the G strength. And then the subleading one, which is still suppressed by this exponential term, but further an extra factor of G strength, or 1 over B. So these are known formulas, and we'll hope to reproduce this from string theory using the diagrammatics that we discussed earlier, and to hopefully check that that calculus works. Okay. Yeah. No, it was one-sided. Yeah, good point. Yeah, so more precisely, I guess we should think about it should a full bound solution. It should be a balanced solution of the fermion. That is true, and how can I say this in a few words? So that's definitely the picture, for instance, in the supersymmetric version of this. The closed strings can tunnel to the other side, but those are charged processes. So there's an extra feature in that model. In this case, they do tunnel, and they contribute to, so for instance, to non-perturbative pieces, non-unitary pieces contributions to the S matrix. So for example, if you compute S as dagger, it will not be 1. It will be 1 minus something, which is calculated by this. Yeah. That's true, it's a non-unitary. Okay, so with this preparation, let's get a little bit, I still want to at least describe how the calculation is actually done in practice. So let's see how that goes. So for that, let me first describe let me just define what the CC instanton is. So it's the D instanton in this particular theory. So for that, I need to discuss conformal boundary conditions. Perhaps the familiar ones are those of the free theory. The simplest ones are Neumann and Dirichlet. The second one will be the relevant one. This comes with a continuous parameter, a modulus, the time at which it happens. And for Lugol CFT, I won't describe them in too much detail, but they're also analogous conformal boundary conditions. One called FCCT boundary condition after the discoverers, which is a Neumann type. But the relevant today is CC, hence the name CC, due to some logic that is Dirichlet type. Unlike the free theory, this has no continuous parameter. So in space and picture is the following. The CC boundary condition is supposed to think of being somewhere here in the strong coupling region. And the FCCT is kind of like a D1 ring, or a half infinite ring. But the relevant one is this blue one. This and this. So summarizing, so we have a Dirichlet and the free boson, CC on the Lugol piece, and Neumann in the BC ghosts. And the picture I like to keep in mind again is like drawing our space-time, where the Lugol field is space and time, the x0 is time. That the instanton has just one collective coordinate, which is the specific time at which the instanton occurs. And these are the things that mediate this non-perturbative correct. Okay, as promised, if you remember this fact from Dirichlet boundary condition in free theory, they have this dependence on the collected coordinate e to the I omega x naught. So if we compute any correlation function in any Riemann surface with boundaries like this, we'll pick up a factor of the sum over all of the energies like this. And once we integrate over this collected coordinate, so integrate all the real line, we'll recover delta function, which imposes energy conservation. That's promised at the beginning of the problem. Okay, so let's try to compute the leading order contribution, which is simple enough to do here. Okay, so as we saw, the one thing we need to compute is this 1-point functions because we need them. Okay, so how do we do that? So instanton action we'll just take to be the WKB estimate that we did a little bit ago using the dictionary of one of the string. The normalization factor might be in principle computed by the exponential annulus with the CC boundary conditions of both sides. It's a number, so we won't attempt to compute it in this talk, but has been calculated using insights of string field theory by Sen. And it agrees with what we'll find right now. But for now, let me just describe the actual this 1-point functions that have the closed string insertion. So next. And to do this, one needs to know what the 1-point functions in the presence of this CC boundary condition, the instanton boundary condition is. And here I'll just remind you of the basic tool, which is a nice tool, bootstrap technique to know what this 1-point function is. The main idea here is that in the cylinder diagram with CC boundary conditions on both ends of the cylinder can be viewed in two different ways. One, as a transition amplitude between two boundary states exchanging a closed ring. And the other viewpoint is as a partition or a trace over the Hilbert space, partition function, over the open string spectrum. Like this. And perhaps a bootstrappy definition of what this boundary condition is that this open string spectrum is the simplest thing it could be, just the identity operator together with its zero solar distance. Okay, so from this definition, you can deduce what this 1-point function is. And I'll spare you the details, but the answer is a simple function, the hyperbolic sign, where the omega is the energy of the incoming. Okay, like this. So the 1-point function is denoted by psi cc. Okay, so we have that ingredient. So we're now ready to compute the leading order non-perturbative contribution to the scattering of the decay amplitude of one closed string into any closed string. It takes this form, just a product of this hyperbolic signs in this form. So compared to the answer from the dual side of the theory, we can fix this precise coefficient to be 1/8 pi squared, negative 1/8 pi squared, okay, which has been reproduced using insights from string field theory. Okay, so this was simple enough that I could describe it even in just a few slides, but perhaps slightly more involved, but also very interesting, is the subleading correction. So still suppressed exponentially, but with a further suppression factor of D string. So this involves more interesting diagrams of higher topology, like the discipline function, as well as the annual 1-point function, and bringing down this empty diagram as well. Okay, so we know how to compute this already, just hyperbolic signs. Now I'll attempt to describe how to compute these two in practice. Okay, as perhaps familiar, way to do this, we have to integrate over the moduli space of this diagram. So we can use three conformal Killing vectors to fix, say, the position of one of the closed strings, and at least the real part of the second vertex operator. So we're left with one modulus. Here, the distance from the boundary and to the second vertex operator. There's one non-trivial integral that has to be computed, the modulus. And perhaps it's not important to take into account the precise factors here, but it's just to remind you that this is a correlator in the ghost piece and the free boson piece. And this is a perhaps challenging part, the Google this two-point function. So for this, I told you that I already specified the entire data for Google CFD. That in principle, this should be already computed from what I described earlier. And that is true. We can expand this correlation function into ingredients that we already discussed. And we can do it by doing a conformal block decomposition. One channel is the one pictured here. This is the boundary channel, where we expand the vertex operator by bringing it to the boundary like this. And as I said, the CC boundary condition only has the identity propagation at the boundary. The other channel is when we bring these two together, the bulk channel. So we have this DOCC formula factor here together with a one-point function. So I'll put it here in gray just to convince you that it's something very explicit. This is supposed to be the two factors of the this one-point functions here and an appropriate Virasoro conformal block. Similarly, in this case, it's slightly more involved because we have to integrate with all possible intermediate states, but it's similar structure, DOCC formula, another structure function, and an appropriate conformal block. And unfortunately, we don't have like a very nice and explicit formula for these conformal blocks, but can be computed very efficiently with something called the sum logic of recursion equation. Okay, yes, so you might try to put this in a computer already, and if you're familiar with string amplitudes, you run immediately into the problem that actually is divergent. So first of all, we have to discuss divergences of this diagram. So in one channel, the bulk channel is just convergent, so let me skip that. In the boundary channel, it turns out that it behaves like this, which is the picture that I was referring to earlier, where there's a degenerated strip when we bring one operator to the boundary, to this boundary channel. And there's two. One is a tachyon state, and we recognize it is. So it's a power divergence. This is a bit more familiar from other types of string theories. We know how to regularize divergence. And this is the logarithmic divergence that I was referring to as well earlier. This is massless state, which leads to log divergence. So it's like 1 over y integral over y. Okay, so this is the thing that, for example, if you choose to cut off, might lead to an ambiguity. Okay, so so now we subtracted familiar, and this one will also subtract it, but cancels with the analogous thing in the annulus amplitude. Okay, so just to show you, this is what you should actually plug into your computer. So subtracting the divergent pieces here, and then compute. And this is manifestly finite, and you can now compute. Okay, so one can do the similar analysis for the annulus one-point function, which one fully described and fully kill. This is slightly more involved, but since the modular space is slightly higher dimensional, but you can expand it into Virasoro conformal blocks as well on the torus, so slightly more complicated blocks. And this type of blocks have only been, recursion relation for these blocks has been only been written down slightly more recently in 2019 as well. But the technology is available, so it's still now we can now do these type of computations. And analyzing the divergences as well, in the open string channel, the picture that I alluded to earlier, where there's a degenerated strip here, we recognize, so let me put it here again in gray, that it precisely cancels the one with the disk, the disk 2.1. As long as we correctly identify the modulus in each side. Okay, so this is the cancellation divergences. As I said, this is like some example that string theory is rather smart. Okay, that's important. And let me just finish here. This is like a pretty ugly expression, but just to convince you that you can plug it in into a computer. Okay, these are just the distant function, the end of one function, and the other empty diagrams that also won't compute, but is some constant c. These are the regularized diagrams. So we subtracted divergent pieces here. And the divergent pieces will separate them and give them some name, some constants that through the formalism that I described, the diagrammatics that I described, we don't know how to fix this constants, but we'll see in a bit. We'll just fix them by comparing to the known answer. So this is a known answer. So we can compute them directly using all this conformal plot decomposition. So the red ones are data points, and the blue one is this function here, the known function. And it agrees pretty nicely as long as these constants of the take the following values. So some log 4, half, 0, and 0. So we reproduce this whole slightly complicated function as long as we fix these constants to be this. And one thing that I want to, at least as in anticipation to Atrox and Stark, these constants have also been reproduced from the string field theory analysis, so that now we don't have to cheat by fixing it by comparing to the matrix model. So a fully independent calculation of string theory has been now done. Yeah, okay, but yeah, this will be the subject of sense talk. Okay, so let me just summarize. So I described kind of like the follow your nose approach of instanton diagrammatics and how it works in the specific example of two-dimensional string theory. We also I also try to emphasize how like this worldsheet diagrammatic seems to be incomplete in the sense that there's some ambiguities that at least so far we don't know how to resolve purely in the onto formalism string theory, but has been resolved with string field theory. So it really points that perhaps string field theory it's a better framework to decode what string perturbation theory is computing. Another lesson is that, well, I described the instanton calculus in this simplified model of two strings, but it's been applied, of course, to other types of string theories, for instance, 10-dimensional superstrings and string compactifications, etc. And well, this thinking about it from the 2D holographic duality, it also provided nice evidence that the duality holds non-perturbatively as well. Okay, and one last slide, just of recent developments. What I alluded to earlier, that for instance, one can apply this calculus to higher dimensional superstrings, now more realistic theories, 10 dimensions. Here, the one comment I want to do is that it's a slightly, perhaps the need for string field theory is a bit more drastic, because if you do the on-shell calculation, you get a result. One of these constants is in some point tension with supersymmetry, with the prediction from supersymmetry of Green and Gupperl, for example. So to really get it right, you really need to use that string field theory. So at least to me, it was it's a little bit more shocking that it's now it's really this calculation really makes it more drastic than with string field theory. Okay, but of course it's been applied to other types of theories. So for instance, compactifications, including new results that are not known from a dual dispersion by Ashok Sen and collaborators. It has been applied to other types of lower dimensional strings, like the minimal string theory, or signed-with string theory, or supersymmetric versions of this 2D string theories. And in fact, this was very useful to resolve one tension that was found earlier with the 2D string theory results that I showed you before. And finally, has been also, like, since the leading order contribution was actually fairly simple to compute, just this one-point function, it's at least the leading order one has been kind of useful to test proposals of new strings and new dualities as a test, a non-perturbative test that the dualities hold. For example, the Virasoro minimal string and another two-dimensional string. But that would be a subject for another talk. So let me end here with this picture that I like to keep in mind of the instantons. So thank you.
So, try to think, or maybe you have some guesses how this corridor shift integrals would collapse to very simple functions. You checked.
Yeah. How this like complicated integrals over conformal blocks and so on reduced to just a part of this hyperbolic sign. So, yeah, no, I mean, I don't have a good intuition for that. It seems to be some sort of magic of low dimensional string theory. From the direct computation of string theory, it looks like a horrible mess, and it is a horrible mess. But somehow the actual results at the end of the day are simple or accuracy. I don't really have a good answer for that. But that seems to be the case for not just this one, but many other types of low dimensional string theories. It usually is a more, it usually is a simpler description. In those cases, it's like the dual holographic.
There should be some secret to structure.
Yeah, that should be. And I think the best answer is that that is uncovered by the holographically dual here. But in the direct one, it's not so obvious. Let's see. So not in this particular model that I discussed because it's non-unitary. But for instance, if you consider a unitary theory, say a supersymmetric version of it, you can, by knowing information of the perturbative piece, that's not quite right. So you can fix just by unitarity some pieces of the non-perturbative corrections of amplitude. So yes, but you cannot fix the full function. But yeah, you can use unitarity in some cases.
Thank you.
Yeah.
So in the sequence one string theory, is there a way to see that schedule is done without knowing the
Well, one answer I would say is that you can do this corrections and then you check S dagger S and check that it's not quite one, but have this extra e to the 1 over G string things that do not saturate the data. So that would be one way to do it, but it's
higher latency now? Is it possible that it comes in?
no, I don't think so.
It's not.
Yeah.
Speaker again.